Hello, and welcome to a new video on Cantera. Today we will learn on how to calculate equilibrium constants for a reaction or for several reactions. Um, and in Cantera, this is actually really simple. It's literally a one-liner, and we'll see how to do that. So today we will look at a couple of more functions, not too many, just 3 extra functions. And see how to use how to calculate the equilibrium constant, and then we will also do a simple check to see if Cantera is actually calculating the right number. Um, as you already should know, equilibrium constant is a very important concept in chemical kinetics. It gives you an idea about the nature of the reaction in the current circumstance, in the given conditions of temperature and pressure and so on. So basically, equilibrium constant is a ratio of the forward rate constant and the reverse rate constant. So if the equilibrium constant has a value of greater than 1, that would mean that in the current conditions, forward rate is being favored. If it is less than 1, then the reverse rate is dominant. And when we achieve chemical equilibrium, that is when the equilibrium constant is equal to 1. So that's there. And also reactions, as you already know, chemical reactions are temperature dependent, and so reaction rates are temperature dependent. And since equilibrium constants give an idea of the reaction rates, equilibrium constants are also temperature dependent, because they are a ratio of the forward reaction constant to the reverse reaction constant. And so we'll take a look at how to calculate the equilibrium constant for a reaction, and then also see how it changes with different conditions. So let's quickly jump into Spider, and we will run individual code lines, individual code in the Python console, because we would like to follow the execution of each and every line. So let's first start with importing Cantera. Import Cantera as CT, and then define a phase. So gas equals CT dot solution. Let's again keep it simple and use the GRI mechanism, GRI 3.0 YAML. All right, now let's set, and again, just to keep it simple, I mean, the main emphasis here is to convey the concept of equilibrium constant. And so let's have a standard, say, a stoichiometric mixture of methane and air. We'll have gas dot set equivalence ratio 1, and then we will have CH4 at 1, and then we will have O2 at 0.21, right, and then N2 at 7.9, and there. All right, so let's see, what do we have here? Okay, so by default, a mixture is at 300 Kelvin, and we have oxygen, methane, and nitrogen. All right, so now let's quickly choose a reaction. So I'll bring forward the GRI mechanism. Sorry. So here is the GRI mechanism, and this is the reaction section of the input data file, and this is GRI 30.yml. So let's pick a reaction. Say, let's say this is 11, reaction number 11, which is oxygen atom plus CH4 gives OH radical plus CH3 radical. So this is reaction number 11 in the GRI input file. So in Cantera or in Python, the index will be 10, because Python, the index starts with 0. So let's go here and calculate the equilibrium constant for this reaction number 11. So all that we have to write is gas dot equilibrium constants, and then give the index of the reaction. In this case, this will be 10, because like I said, the index starts with 0. So the 11th reaction will be number 10 here. And so that's the equilibrium constant. Let's also save this equilibrium constant somewhere so that we can do some checks on this. So let's EQC or something. All right, so let's do this. EQC. Now, if you see in the variable explorer, EQC, the value is being displayed as 0.355. We can also just quickly write EQC and it will display the value of this variable also. And now let's calculate the forward reaction coefficient for this reaction. So forward, so FWC, or yeah, FWC equals gas dot forward rate constants, and now input 10 again. So this is a forward rate constant, and then we can do the same thing for reverse rate constant. So RWC equals, and I just hit the up arrow because Spider retains the history of commands that you've run. So we can just say forward. Oh yeah, okay. So here we will say reverse rate constant. So that's RWC. Right. Now we see EQC is equal to 0.355. Now if we do FWC by RWC, so it gives a value of 3.35589, which is exactly equal to the equilibrium constant that we calculated here. So what we've done is we first calculated the equilibrium constant, and then we found out the ratio of the forward and the backward rate constants, just to check if Cantera is giving Cantera is actually calculating the right thing. And we see that it is exactly right. So now let's also change the condition of the reaction. So maybe raise the temperature a bit. So gas dot TP equals, say, 500, and keep the same as 1 atmosphere. So CT dot 1 atmosphere. All right. Now let's repeat the same exercise and see what happens with the change in temperature. So just hitting the up arrow, again calculating equilibrium constant. Now if I find out, see, so the equilibrium constant has changed from 0.355, it is now 2.648. Let's again calculate the reverse and the forward rate constants as well.
This might answer your question. A delivery or ball in cricket is...
Sorry, for some reason, Alexa decided to chime in as well and give some piece of advice. But anyways, let's continue with where we left off. So okay, so now we raise the temperature to 500 Kelvin, and let's now calculate the forward reaction rate constant. So we have the forward rate constant. Now let's do the same thing for the reverse rate constant. And now again, let's just find the ratio of these two constants. So FWC by RWC. So see, this is exactly equal to what Cantera calculated as equilibrium constant. So this is all a simple check. And so this is how you calculate equilibrium constants in Cantera. It's really, really simple, as you've seen. One thing, however, is that you can only calculate the equilibrium constants for reactions that are a part of the reaction mechanism. So you can calculate the equilibrium constant for any of the 325 reactions from from GRI mechanism. However, if you were to have a different reaction that is not a part of GRI, then either you will have to import a reaction mechanism where that particular reaction is present, or you will have to generate a new YML file like we've seen in the previous sections, with including the new reaction rate, or the reaction rather, with the Arrhenius constants and everything else in there. That's the second approach. The last or the third approach is also, I mean, without creating a YML file as such, you can just add reactions to Cantera. But that is a slightly advanced topic, and we'll see if we can cover that too at a later stage, but not right now. Right now, let's just limit ourselves to calculating equilibrium constants to the reactions that are available in the reaction mechanisms. So that's it, and I'll see you in the next video. Thank you.